You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. A pattern library in artificial intelligence can be understood as a structured collection of reusable design strategies that practitioners apply when building or managing systems. Rather than inventing new solutions for every challenge, engineers and leaders draw upon established patterns that have already been tested and proven. This approach mirrors practices in fields like architecture and software engineering, where pattern libraries ensure consistency and reduce risk by capturing shared knowledge. In AI, the rapid pace of innovation makes patterns especially valuable, as they provide grounding in principles that remain steady even as technologies evolve. A well-organized library transforms scattered lessons into structured guidance, turning individual insights into reusable wisdom. By treating these strategies as patterns, organizations ensure that best practices are not lost but embedded into the fabric of AI development. The importance of patterns lies in their ability to help practitioners avoid starting from scratch. Each AI deployment involves a complex blend of models, data, infrastructure, governance, and human interaction. Without patterns, teams must solve the same problems repeatedly, reinventing solutions and risking mistakes. Patterns provide shortcuts, offering reliable designs that capture the hard-earned lessons of prior deployments. They also support communication, giving teams a shared vocabulary to describe common challenges and solutions. For example, instead of explaining an entire retrieval pipeline from scratch, one can refer to the retrieval augmented generation pattern, instantly invoking a body of shared understanding. Patterns thus save time, reduce risk, and accelerate adoption, while also embedding responsibility and consistency into the design process. Retrieval augmented generation, or RAG, is one of the most widely applied patterns. RAG combines vector embeddings, indexes, and generative models to produce answers that are grounded in external knowledge. Instead of relying solely on what the model learned during training, RAG retrieves relevant documents or chunks of data and integrates them into its outputs. This approach improves accuracy, reduces hallucination, and creates pathways for attribution. It turns generative systems into knowledge-aware assistants, capable of answering questions based on curated sources rather than vague memory. In enterprise settings, RAG has become the backbone of compliance-sensitive applications, ensuring that outputs can be tied to verifiable data rather than untraceable probabilities. The key components of RAG are embeddings, chunking, retrieval, and attribution. Embeddings transform text or other content into numerical representations that capture meaning, enabling efficient similarity search. Chunking breaks large documents into smaller sections so that retrieval focuses on manageable units. Retrieval then selects the most relevant chunks, passing them to the model for integration into its output. Finally, attribution ensures that users can trace claims back to their sources, fostering trust and transparency. These components work together to create a cycle of input, grounding, and output that transforms generative systems from opaque engines into tools of reliable reasoning. Without any one of these components, the RAG pattern loses effectiveness, showing how essential the balance of design elements is to AI performance. The strengths of RAG are clear. It improves trust, transparency, and accuracy by anchoring outputs in real data. Users gain confidence because they can verify claims. Regulators gain assurance because compliance can be demonstrated, and organizations gain reliability because outputs are less prone to hallucination. RAG-E also allows continuous updating, since retrieval systems can be refreshed with new documents without retraining the model itself. This agility makes it especially useful in fast-changing fields like finance or healthcare. By combining static intelligence with dynamic retrieval, RAG balances stability with adaptability. Its strengths explain why it has become one of the most widely adopted patterns in enterprise AI. The limitations of RAG highlight its dependence on the quality of data and indexing. If the retrieval database is outdated, incomplete, or biased, the outputs will reflect those flaws. Similarly, poor chunking strategies may fragment meaning, leading to irrelevant or misleading retrievals. Attribution, while valuable, can also overwhelm users if references are inconsistent or overly technical. RAG does not eliminate the need for careful curation, it amplifies it. Enterprises must therefore treat RAG as a pattern that requires governance, not as a shortcut that solves accuracy automatically. Recognizing its limitations helps organizations deploy it responsibly, ensuring that its power is matched by oversight. The agent pattern represents another major design strategy, one focused on orchestration and automation. Agents differ from simple pipelines in that they plan, execute, and coordinate multiple tools or systems to achieve tasks. They break down objectives into steps, call APIs or databases, evaluate results, and iterate until goals are reached. Agents can therefore manage complex, multi-step workflows that go beyond single queries. They embody the principle of autonomy, handling sequences of tasks that would otherwise require human coordination. The agent pattern reflects the aspiration of AI not just to respond but to act, creating systems that collaborate with humans to accomplish goals. The strengths of agents lie in their ability to automate multi-step processes and reduce human workload. For example, an agent might research a question by retrieving documents, summarizing them, and drafting a report, tasks that would otherwise require multiple people or hours of effort. In enterprise contexts, agents streamline compliance reporting, automate routine IT workflows, or orchestrate customer service interactions. Their strength is versatility, adapting to varied tasks while integrating diverse systems. Agents thus extend the impact of AI beyond single answers into continuous assistance, creating value through automation and coordination. The weaknesses of agents reveal why they remain a developing pattern. Agents are resource-intensive, often requiring many steps, retries, and API calls, which drive up cost and latency. They can also be unreliable, failing to complete tasks when conditions shift or when assumptions prove wrong. Debugging agents can be complex, since failures may occur at any stage of planning, retrieval, or execution. Without careful monitoring and guardrails, agents risk acting unpredictably, creating trust concerns. Their promise is great, but so is their risk, making the agent pattern one of the most powerful yet challenging designs in the AI toolkit. Evaluation frameworks represent another critical pattern, ensuring that AI systems are measured systematically for correctness, reliability, and fairness. Evaluation provides the evidence that systems are not only functional, but also trustworthy. Frameworks can involve curated golden sets of reference data, rubric-based human scoring, or LLM as-judge approaches for scalability. By embedding evaluation into the lifecycle, organizations ensure that improvements are genuine and that risks are detected early. Evaluation is not optional but foundational, as it connects AI practice with accountability. Without evaluation, claims of performance remain speculative, leaving organizations vulnerable to failures or misuse. Golden sets and rubrics represent the most established evaluation practices. Golden sets provide ground truth by collecting carefully labeled datasets that serve as benchmarks. Rubrics provide structured scoring guides that enable consistent human evaluation, ensuring that subjective judgments are captured systematically. Together, they anchor evaluation in shared standards, reducing noise and bias. They also provide defensibility, as organizations can point to clear evidence when regulators or stakeholders demand accountability. Golden sets and rubrics remind us that evaluation is not only about metrics but also about governance, ensuring that AI outputs meet expectations of fairness, safety, and quality. Safety and guardrail patterns provide reusable strategies for ensuring responsible AI behavior. These include allow and deny lists, which define what content is acceptable, policy engines that enforce domain-specific rules, and safety levers that filter or block unsafe outputs. These elements can be applied flexibly across different contexts, ensuring that systems remain aligned with ethical and regulatory expectations. By treating guardrails as patterns, organizations create toolkits that can be reused across projects, embedding safety by design. Safety is not a one-time adjustment, but a continuous process of alignment, and reusable patterns make it possible to implement consistently. Observability and monitoring form another pattern, ensuring that systems remain reliable by tracking prompts, outputs, latency, and failures in real time. Observability provides visibility into how models behave under actual workloads, allowing teams to detect drift, degradation, or misuse. Logs, spans, and traces capture data that inform debugging, compliance, and optimization. Observability is essential for maintaining trust, as it enables organizations to prove that systems perform as intended and to intervene quickly when they do not. It transforms AI from a black box into a monitored, accountable system. Reliability patterns provide further safeguards, such as timeouts, ID impotency, and transactional prompting. Timeouts prevent cascading delays when systems stall. ID impotency ensures that retries do not create unintended side effects, and transactional prompting structures outputs to guarantee closure. These patterns reflect principles borrowed from software engineering, adapted to the specific challenges of AI. They ensure that even when failures occur, systems degrade gracefully rather than catastrophically. Reliability patterns embed resilience into AI systems, turning fragile pipelines into robust services that can withstand real-world conditions. Taken together, these patterns, RAG, agents, evaluation frameworks, guardrails, observability, and reliability, form a foundation for responsible AI adoption. They are not isolated techniques, but interconnected practices, reinforcing one another to create systems that are accurate, transparent, safe, and resilient. In the next section, these patterns will be consolidated into audio-friendly checklists, providing simplified summaries that make them easy to remember and apply in practice. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Checklists are simplified pattern summaries that help practitioners recall and apply complex strategies without revisiting entire design documents. They work especially well in spoken or audio-first formats, where concise reminders reinforce learning in practical, memorable ways. Much like pilots or surgeons use checklists to ensure critical steps are never overlooked, AI practitioners can rely on them to embed consistency into design and deployment. A checklist distills patterns into their essentials, making them portable and repeatable. In practice, they serve as both memory aids for experienced teams and onboarding tools for newcomers, bridging the gap between theory and execution. By framing pattern libraries into spoken checklists, organizations create practical tools that reinforce safe, efficient, and trustworthy AI practices. The WARAG checklist distills retrieval-augmented generation into 5 spoken essentials. First, embeddings, which transform inputs into meaningful numerical representations. Second, chunking, which breaks content into manageable pieces for precise retrieval. Third, indexes, which organize embeddings into searchable structures. Fourth, retrieval, which selects the most relevant chunks for the model to use. Fifth, attribution, which ties outputs back to sources, creating transparency and trust. When spoken together, the checklist is embeddings, chunking, indexes, retrieval, attribution. This short sequence reinforces the logic of RAG without requiring detailed explanation, allowing practitioners to recall the steps quickly during design or troubleshooting. It captures the essence of RAG while remaining easy to memorize. The agent checklist summarizes the core steps that agents perform when orchestrating tasks. First, plan, as agents must break down goals into actionable steps. Second, execute, as they carry out those steps using tools or APIs. Third, monitor, as they observe progress and check whether actions are working as intended. Fourth, retry, since agents often need to recover from failures or adjust strategies when conditions change. Fifth, review, as agents or their human overseers must evaluate outcomes and confirm success. Spoken together, the agent checklist becomes plan, execute, monitor, retry, review. This structure helps teams remember that agents are not just about automation, but about structured, monitored workflows that include resilience and oversight. The evaluation checklist provides a compact summary of how AI systems are assessed. First, ground truth, which anchors evaluation in curated datasets or authoritative references. Second, metrics, which quantify correctness, reliability, or fairness. Third, human or LLM judges, which supplement automated scoring with nuanced evaluation. Fourth, continuous loops, which ensure that evaluation is not a one-time event, but an ongoing process. Spoken together, the checklist becomes ground truth, metrics, judges, continuous loops. This format reinforces that evaluation is about both rigor and iteration, embedding accountability across the lifecycle of AI systems. The spoken rhythm makes it easier to recall during planning or audits, ensuring that evaluation remains central rather than peripheral. The safety checklist highlights reusable strategies for protecting users and organizations. First, guardrails, which define broad constraints on outputs. Second, policy rules, which encode domain-specific requirements such as compliance with law or industry standards. Third, sensitive data filters, which prevent PII, PHI, or other protected information from being mishandled. Fourth, oversight, which ensures that human review and monitoring remain in place for critical applications. Spoken together, the checklist is guardrails, policy rules, sensitive data filters, oversight. This sequence reinforces the idea that safety is not achieved through one mechanism but through layered protections, reminding practitioners to embed safeguards into every stage of design and deployment. The performance checklist emphasizes strategies that keep systems efficient at scale. First, caching, which reduces redundant computation by reusing prior results. Second, batching, which consolidates requests for efficiency. Third, streaming, which improves responsiveness by delivering outputs incrementally. Fourth, concurrency, which enables multiple requests to be processed simultaneously. Spoken together, the checklist is caching, batching, streaming, concurrency. This compact pattern reminds practitioners that performance is not about a single technique, but about orchestrating multiple approaches to reduce cost, latency, and inefficiency. It serves as a practical reminder that engineering choices directly influence user experience. The cost checklist captures strategies for financial sustainability. First, monitor tokens, since token consumption often drives expenses in hosted language models. Second, prune workloads, removing unnecessary queries or requests. Third, demonstrate ROI by connecting savings or efficiency gains to organizational outcomes. Spoken together, the checklist is monitor tokens, prune workloads, demonstrate ROI. This concise pattern reinforces that cost engineering is about awareness, efficiency, and communication, ensuring that financial considerations remain as central as technical ones. In spoken form, the checklist makes it easy for leaders and engineers alike to recall the essentials of responsible AI budgeting. The governance checklist distills organizational responsibilities into 4 essentials. First, privacy, which safeguards PII, PHI, and sensitive data. Second, copyright, which ensures respect for intellectual property. Third, contracts, which define obligations and vendor relationships. Fourth, compliance, which aligns adoption with regulatory requirements. Spoken together, the checklist is privacy, copyright, contracts, compliance. This rhythm captures the centrality of governance in AI adoption, reminding practitioners that technical success must be matched with legal and ethical responsibility. It also emphasizes the shared role of technologists, legal teams, and executives in ensuring AI is adopted responsibly. The deployment checklist emphasizes organizational practices that support adoption. First, pilots, which test systems in controlled settings. Second, training, which prepares users to adopt tools responsibly. Third, change management, which coordinates people, processes, and culture. Fourth, feedback loops, which allow continuous improvement. Spoken together, the checklist is pilots, training, change management, feedback loops. This spoken pattern emphasizes that deployment is not only technical but also organizational, requiring structure and support to succeed. It reminds teams that successful adoption is measured by human alignment as much as by system performance. Future-oriented patterns capture emerging research directions that may shape the next generation of AI design. These include adaptive retrieval, which dynamically adjusts what information is pulled based on context; hybrid agents, which combine symbolic reasoning with neural generation for greater reliability; and evolving guardrails, which use AI itself to adapt safety filters as new risks emerge. While less mature than established patterns, these directions highlight the evolving nature of pattern libraries. They remind practitioners that the library is not static, but dynamic, continually expanding as innovation and regulation shape the field. Mentioning them in checklists prepares organizations for change, encouraging forward-looking adoption strategies. Enterprise relevance is perhaps the strongest justification for maintaining spoken pattern libraries. Organizations often face the challenge of scaling AI across diverse functions, and pattern libraries provide accelerators that reduce risk and improve consistency. Checklists allow executives to engage in oversight without requiring deep technical expertise, while giving practitioners tools for recall during design, governance, and troubleshooting. They also facilitate audits, since structured checklists align with compliance requirements. For enterprises, pattern libraries are not optional but essential, as they transform scattered best practices into coherent strategies that scale responsibly. Cross-domain value demonstrates that pattern libraries extend beyond AI engineering into regulated industries like law, medicine, finance, and education. RAG patterns ensure grounded answers in compliance-sensitive contexts like legal search. Agent patterns automate multi-step workflows in healthcare or finance. Evaluation and safety checklists align AI with fairness and transparency in education. Governance checklists support compliance in global enterprises. The universality of these patterns shows that they are not bound to one industry but apply broadly, adapting to specific contexts while preserving shared principles. Cross-domain adoption reinforces the value of codifying patterns, since they provide stability across diverse applications. As the recap concludes, it is clear that spoken checklists transform the lessons of pattern libraries into practical tools for recall, training, and governance. They capture RAG essentials embeddings, chunking, indexes, retrieval, attribution. They summarize agent practices: plan, execute, monitor, retry, review. They condense evaluation into ground truth, metrics, judges, continuous loops. They define safety as guardrails, policy rules, sensitive data filters, oversight. They remind us of performance caching, batching, streaming, concurrency. They protect cost engineering, monitor tokens, prune workloads, demonstrate ROI. They guide governance, privacy, copyright, contracts, compliance. And they ensure deployment pilots, training, change management, feedback loops. These spoken forms reinforce learning, ensuring that patterns remain accessible long after formal study. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.